Right, we are discussing the cosmic background radiation, and the first observable feature I've discussed in some detail was the Planck spectrum. The fact that the spectrum fits to an extremely high, with an extremely high accuracy, a black body spectrum. And the temperature, as you all know, I'm sure you knew before, that this corresponds to something like 2.73 kelvins. And if you know the temperature, and if you know that it is black body radiation, then this gives you immediately the density, the energy density by the Stefan-Boltzmann law. So we have that was an important consequence. We get the density parameter for the radiation, which is energy density, or the mass recalculated as a mass density of the radiation divided by the critical density. So this here is determined by the Stefan-Boltzmann law in terms of the temperature, and this here is essentially the Hubble constant squared. Yeah, the critical density is up to a factor gravitational constant and velocity of light. Up to that, it is just the Hubble constant squared. And the Hubble constant is also fairly well known. So we can calculate this quotient, and we get that this is smaller than 10 to the minus 4. And that's an important, that's a very, very strong statement, because the assumptions which went into this were very few. Yeah? It was just the observation that we have a black body spectrum with this temperature and the value of the Hubble constant. And yeah, this is very difficult to doubt, either of these statements. So they are very sure that the density parameter of the radiation is that small. So if you compare this with the density parameters for matter and for the lambda, which we needed in order to match the supernovae data, which were 0.7 and 0.3, so we see that the omega r is negligible in comparison to that. So we live in a universe which is dominated by a cosmological constant and by matter, which can be modeled as a dust, to all we know. So this was one important consequence we have found last time. And then we have talked about this hypersurface of last scattering. So the idea was that if we now observe a Planck spectrum, then apparently this has come into existence as a Planck spectrum, and then the photons just propagated freely. So we have calculated how the temperature changes if the photons propagate just freely. So the temperature is inverse proportional to the scale factor. And this means that we have a relation between the scale factor and thereby with the redshift and the temperature. So if the cosmic background radiation moved from a time TE to a time TO, TE is the time when the radiation came into existence, when the universe became transparent, TO is the time now, and then we can calculate from the temperature, which is known here, we can calculate the temperature at this time. And under the simplifying assumption that the universe became transparent at about the time of a typical recombination energy, which is about 1 eV. We have calculated a rough estimate for the temperature, and a more precise calculation gives that the temperature at this time TE, where the photons decoupled, is approximately something like 3,000 or 4,000 kelvins. Yeah. So during the time when the photons of the cosmic background radiation traveled from this hypersurface to us, the temperature dropped from this temperature to about 7.3 Kelvin, just as a consequence of the expansion of the universe. And you can calculate the redshift factor between these two times. So this corresponds to a redshift of approximately 1,100. So that's the redshift of the photons in the cosmic background radiation.
May I ask a question?
Sure.
I mean, how come when reconcile this with their conservation of energy? So we first had photons which were highly energetic, and now we have them with a very low energy. Does it mean that they somehow gave the energy to gravitational field?
Well, remember what we did when we considered the radiation-filled universe. Actually, we calculated the energy conservation law for this. Energy conservation means divergence of energy momentum tensor is 0. Yeah? This does not necessarily mean, but in this case it does mean, that we have a conserved quantity in the sense d by dt of something is 0. We have talked about this. For a general perfect fluid, actually, we cannot put it into this form, but for the radiation, we can put it into this form. And actually, this relation between the time, the evolution of the time, and the evolution of the scale factor, of the density and the scale factor. The density and the scale factor. That's the density, if I go backwards in time, grows for radiation with a fourth power of A, was a consequence of this conservation law. So in this sense, also the Stefan-Boltzmann law, which is the same thing if you just express the scale factor, the ratio of the scale factor in terms of the temperature, is in perfect agreement with this conservation law. Conservation law, in the sense, divergence of energy momentum tensor is 0. Which means that locally no energy is produced. Yeah? It does not necessarily mean that in a certain volume the energy is constant. These are two different things. Okay? So it is in agreement with conservation of energy. What did I want to say? Yeah, I think these were the essential things we have discussed last time. And yeah, maybe I should say, when I say that the photons traveled freely from here to here, of course, this is an idealized way of looking at it, but a very good approximation, actually. First of all, it was not a precise, sharp time where the universe became transparent. It was something like a certain period of time when then gradually the universe became transparent. So scattering became more and more rare. And the second thing is that, of course, not all the photons travel from here to here really without any effect from other matter. From time to time, one of them is scattered, but this is very rarely. And actually, these very rare events, they have been observed from photons which pass through galaxy clusters where I have a fairly high density. Yeah, where I have, in particular, where I have a hot plasma, and the photons are then scattered at the electrons in this plasma. And this gives rise to a certain very slight distortion of the Planck spectrum, which has been observed for a couple of galaxy clusters. This is known as the Sunyaev-Zeldovich effect. I will briefly talk about this when we speak about perturbation theory. So I just wanted to mention that this is not precisely true that the photons travel freely, but it's a very good approximation. Actually, if you calculate the mean free path or the mean or the flight time of a photon, the average flight time of a photon before it is scattered at some particle in our universe, you find that this time is bigger than what we believe is the age of our universe. Yeah? So the vast majority of all photons never encounter any scattering process. They are just traveling freely in this period. Of course, in the early periods, they do encounter lots of electrons, and they do undergo scattering. Okay, that was the Planck spectrum. And what I want to discuss today is anisotropy, which was a main field of research as far as the cosmic background radiation is concerned over the last decade or so. So the first observation is, of course, that the anisotropies are very, very small. Yeah, so the cosmic background radiation is isotropic to an extremely high degree. So what do I mean by isotropy of the cosmic background radiation? We have said we observe a Planck spectrum, and we observe a Planck spectrum in every direction. Now the question is the temperature the same in every direction? Yeah, a Planck spectrum is characterized by a certain temperature. The temperature tells us where the maximum is, or the other way around, the maximum tells us which temperature it is. And we can now ask, is the temperature in this direction the same as the temperature in this direction? And the answer is yes, to a very high degree. So the cosmic background radiation is isotropic to within 10 to the minus 5. Yeah, so that's a relative change. So delta T over T. Yeah, if I look at 2 points, measure temperature in this direction, temperature in this direction, take the difference and relate it to one of the 2 values, then I get something which is smaller than 10 to the minus 5. And so this is isotropic to a very high degree. But the anisotropies have been measured. They were first measured by the COBE satellite around 1990. And then with a much higher accuracy by the more recent satellite projects, WMAP and Planck. So it was the main purpose of WMAP and of Planck to measure with a very high accuracy these temperature variations in the sky, the anisotropies in the sky. So in which way would you formalize this? So you have a temperature now. So the temperature is the function on the sky. The sky is a sphere. So the sphere can be parameterized with coordinates theta and phi. Or to put this another way, every point in the sky corresponds to a unit vector. Yeah? So I write it in this form. So the temperature becomes now a function of which varies over the unit sphere, over the set of all unit vectors. So you may write this unit vector, if you choose a basis, in the familiar form as cosine phi, sine theta, sine phi, sine theta, cosine theta. Yeah, you just choose an appropriate axis, then theta is the angle with respect to this axis, and phi is the azimuthal angle. And then every unit vector corresponds to a pair of coordinates theta and phi. So you could also write T as a function of theta and phi. And yeah, the question is, so is this, if this were a constant, then we would say the cosmic background radiation is perfectly isotropic. Yeah? And in which way can we now mathematically capture the anisotropies where we have a function on a sphere? What do you do if you have a function on a sphere? Well, let me begin the other in a different way. If you have a function on a circle, what would you do with that? If you want to analyze a function on a circle is the same as a real line where you identify points which are away by a period of 2 pi from each other. Yeah? So we have a map on the real line, which is 2 pi periodic. And there's a very well-established method to analyze functions of this kind. This is called Fourier analysis. Yeah? You make a Fourier expansion of this function. That's a very natural idea if you have a function on a circle. Now we do not have a circle, we have a sphere. We have the phi coordinate, which we know from the circle, and in addition the theta coordinate. And then you do something which is a little bit more complicated than Fourier analysis. It's an expansion in terms of basis function which depends on theta and phi. And I'm sure all of you have seen this either in electrodynamics, in quantum mechanics, and maybe also somewhere else. This is the expansion in terms of spherical harmonics. Yeah? So this is, in a sense, a generalization from the Fourier expansion to the two-dimensional sphere. Yeah? So what the Fourier expansion or the Fourier analysis is on a circle is the analysis in terms of spherical harmonics on the sphere. And let me just remind you how they are defined. So the expansion of this function of this here in this spherical harmonics. So this is Kugelflächenfunktion in German. Yeah? In German we say Kugelflächenfunktion. English word is spherical harmonics. So we write the T of E as a sum, and the basis functions, they are called YLM usually. These are the spherical harmonics. And they depend on a unit vector, or if you write it in this way, on theta and phi. And then you have expansion coefficients, which I denote now ALM. And the M is an integer index which runs from minus L to L, and the L runs from 0 to infinity. So this is an expansion for a very large, which can be done for more or less any function you can imagine on the sphere. It doesn't work only for smooth or continuous functions. It even works for functions which are just let's say, square integrable or something like that. They may even have discontinuities and things like that. It's exactly the same as for the Fourier expansion. Yeah? Fourier expansion also works for a very large class of curves. So I have to remind you what the y's are. You have to be a little bit careful because different authors define them in a slightly different way. Yeah? So you have to be a little bit careful if you compare with the literature. So what I use, I think it's a convention which is usually used in quantum mechanics. You have a normalization factor, 2L plus 1 over 4 pi, L minus m factorial over L plus m factorial, and then something which is denoted PLM of cosine theta and e to the im phi. So you see, if you don't have a theta dependence, then it is just Fourier expansion. Yeah, Fourier expansion is just expansion with respect to these exponential functions of phi. You could write this as a sum of cosine and sine if you decompose it into real and imaginary part. So this is just the term you're familiar with from Fourier expansion, and then you have these PLMs here. I have to tell you what this is. PLM are the so-called associated Legendre polynomials. You have an argument x, which takes values between -1 and +1, right? Cosine of theta varies between +1 at the north pole and -1 at the south pole. So x is a variable which is defined on the interval -1 to 1. And here comes the point where different authors use different conventions. This factor -1 to the m is sometimes written here, and sometimes it's completely omitted. Yeah, so you have to be a little bit careful with this. And but this is the convention most physicists use. So in geodesy, for instance, they use usually the convention without the -1. 1 minus x squared to the power m half. And dm by dxm. Yes, it's the mth derivative with respect to the argument x of something which is denoted plx. And this is a Legendre polynomial. So these are the spherical harmonics. These are the associated Legendre polynomials. And they are indeed polynomials. You will see in a minute if I write the PL. The PL is defined as 1 over 2 L factorial dl dxl x. I have to read my own handwriting. X squared minus 1, I think, is what this means. I hope that's correct. It's difficult to read. Okay, anyway, so that's Legendre polynomials. So you see, if you differentiate something of this kind, then you get a polynomial, right? So this is indeed a set of polynomials. So the PLs are polynomials, and this is also a polynomial here. And yeah, these are the terms which you use for the expansion in terms of the theta. So why do you not do just a Fourier expansion with respect to theta? Well, because the angle theta has different features than the angle phi, right? Phi is 2 pi periodic, so that's what the Fourier expansion is appropriate for. But theta goes from 1 to, cosine theta goes from 1 to -1, and there's no 2 pi periodicity, so therefore you do something else. You expand it with respect to the powers of cosine of theta. And what you prove is that this set of functions, these spherical harmonics, actually form a basis for an appropriate function space, an L2 space, for instance, set of square integrable functions, and that you can then expand every function on the sphere in this way. And they are orthonormal. Yeah. So if you have if you have the usual scalar product defined by the what you use in quantum mechanics, right? The L2 scalar product. This is just delta M prime delta L prime. So this is an orthonormal set of functions. And it's actually an orthonormal basis, so it's an orthonormal complete set of functions, of square integral functions. Okay, this guarantees that you can write every function on the sphere in this way. The question is, why is it appropriate to write it in this way? Is it helpful? Well, in many cases it is very helpful, and it's always very helpful if you have the Laplace operator in some way involved in the game. So for instance, if you do electrostatics, then you have for the potential, for the electrostatic potential, you have the Poisson equation. So outside of the sources, it's the Laplace equation. So you have to apply to Laplace operator to your potential. And the Laplace operator has a nice property that these are eigenfunctions of the Laplace operator. So you can immediately, you can use a separation ansatz for your potential, and then you just get differential equations for the coefficients, which in this case, of course, depend on R. Yeah, if you have a function of R, theta, and phi, then you have coefficients which depend on R. And because the Laplace operator has these things as eigenfunctions, you get a set of differential equations for the coefficients. In this way, you can solve the Laplace equation. And this is also, of course, what is done in quantum mechanics. So you also have the Laplace operator, right? If you have a Hamilton operator, which is kinetic energy plus potential energy, kinetic energy is essentially the Laplace operator. And then you have a potential, and if you want to solve this for a spherically symmetric potential, then this separation ansatz also works. That's what we do for the hydrogen atom. And as everybody knows, I'm sure these are, as I said, the eigenfunctions of the Laplace operator. And actually, the Laplace operator in quantum mechanics is associated with the angular momentum operator. The angular part of the Laplace operator is associated with the angular momentum operators. And this is a quantum number associated with the modulus of the angular momentum. And this is a quantum number associated with the z component of the angular momentum. So I think in this context, everybody has seen these functions before. And they are also very useful in cosmology. So we just expand our temperature, which can be measured. We observe the cosmic background radiation in any direction. So we measure this function on the sphere. And in order to analyze the anisotropy, we expand it in this form. So of course, then we get something like, let me write the first terms explicitly. Actually, what one expands is usually not, I shouldn't have called these coefficients m. So what one expands is actually, usually it's unanimously done in this way, you divide by the average temperature. Yeah? So you measure the temperature on the sphere, it has a certain average value, and the average value is this TO, and you expand the TO, this divided by TO. Yeah? Then the coefficients are what one usually calls ALM. Okay, so then we get an expansion of this form. So let me write just the leading order terms. So you see if the number of terms here in this second sum, this increases with L. Yeah, for L equals 0, I have just one term. So the L equals 0 term is just this here, y0, 0, which is actually a constant. Yeah? Y0, 0 is a constant. If they are tabulated, right? You can find these in tables, and then you know what it is, and they are also implemented in computer programs like Mathematica and so on. So they are easily under control. So that's a monopole term. Then you have the dipole term where L is equal to 1. If L is equal to 1, m runs from -1 to 1. So this is a term from -1 to 1. And then you have a 1m, the coefficients, y1m of theta and phi. That's a dipole term. And then you have the higher order terms. And yeah, the rest is then L from 2 to infinity, m from minus L to L, ALM, YLM of theta and phi. So now let's look at the terms, at the first two terms, which I've written explicitly separately. So this here is the monopole term, what one calls the monopole term. So it's a constant, yeah? So this is a constant. It does not depend on theta and phi. And well, what is it? Because we have divided by the average temperature. So if only this term would be there, if all these terms would be 0, this would mean T is constant. It's constant over the sky. And if TO is the average, then of course this constant of this quotient must be 1. Yeah? So the monopole term with this convention to divide by T0 or TO or whatever you call it, monopole term, and this is equal to 1. Yeah, must be equal to 1 with this convention. And then we get the dipole term. And the dipole term is interesting. So this has been measured for the cosmic background radiation here on Earth, as it is measured here on Earth already in the late 60s. I think the first measurement was in the late 60s, and then with higher accuracy with balloon experiments in the early 70s. Actually, several groups did this. There was also a priority quarrel between them. The later Nobel Prize winner, George Smoot, was involved in this. When you look at talks by Smoot, you will always say he discovered the dipole of the cosmic background radiation, and other people very strongly argue against this. So there were other people who did it actually before him, and as I claim, with more or less the same accuracy. So there's a certain priority quarrel going on. You can read about this on the internet if you are interested in this kind of discussions. So anyway, it is very well established, and it well, how would you interpret? And actually, it's comparatively big. It's bigger than this. So when I said the cosmic background radiation is limited by this value, I meant after the subtraction of the dipole term. And how would you interpret this? As you have a fairly big dipole term, which was measurable already around 1970. So what does this mean? It means a dipole symmetry means there's a particular axis. Here's the axis of the dipoles. Think of electrodynamics, positive charge, negative charge. Yeah, that's a dipole. And then you have, positive charge predominant on one half axis, negative charge predominant on the other half axis. Here's the same with the temperature. So you have a little bit colder than the average in this direction, a little bit warmer than the average in the other direction. Yeah, that's what the dipole anisotropy means. You have an idea where this comes from, how you could explain this? Such a dipole anisotropy in the cosmic background radiation? Actually, it was not a surprise when it was discovered. People expected something like that.
It's Earth's motion.
Yes, it's the motion of the Earth, right? So if we are in a perfect Robertson-Walker universe, and this photon gas which makes up the cosmic background radiation is perfectly homogeneous, then not everybody would see an isotropic distribution. Only those observers who are at rest with respect to the cosmic background radiation see the isotropic distribution. These are the standard observers in the Robertson-Walker universe. Here's the T lines. But actually, can we expect to be on a T line in a Robertson-Walker universe? We are on the Earth. The Earth is rotating around the sun. So will the whole cosmos follow this motion around the sun? That's very unlikely, right? So that's the first kind of peculiar motion we have to take into account. Then the sun, with the whole solar system, is orbiting around the center of our galaxy. This, again, will lead to a peculiar motion, which should be measurable. Our galaxy is one member of the local group. The local group is bound together gravitationally, so it has a certain one member has a certain proper motion around the barycenter of the whole group. And actually, we also know that the whole local group is moving through the background. roughly in the direction of the Virgo cluster, which is a big galaxy cluster in a certain direction, not too far away from us, and it's interpreted in the way that the gravitational pull from this Virgo cluster, that this pulls our whole local group towards it. So this combination of all these motions leads to the effect that we on the Earth, we are not at rest with respect to the cosmic background radiation. We are moving with respect to the cosmic background radiation. And this means that if the photon bath would actually be perfectly homogeneous, it would mean that we have a certain blue shift in the direction towards which we move, and a red shift in the direction in the opposite direction. Yeah? So these photons come towards us, they are blue shifted. These move away from us, they are red shifted. And the blue shift means that the temperature is a little bit higher. Yeah, if you take a Planck spectrum and you blue shift everything, then you get something which is where the resulting temperature is a little bit higher than the one before, and in the other direction it is lower. So in the plots of the dipole term, if you see plots of the cosmic background radiation, usually the hotter parts are color-coded in red, and the other ones, the colder parts, are color-coded in blue. That's confusing, because a blue shift corresponds to a hotter point. Yeah? So what is shown red in the picture is actually the point where you have a blue shift, and what is pointed blue is where you have a red shift. It's a little bit confusing, but that's the usual convention. Anyway, this was measured. So you can measure the temperature variation. This means the redshift which is produced, and if you interpret this as a Doppler effect, then you just can calculate it. You can calculate the velocity of the Earth relative to the cosmic background radiation from this. So this is actually what you measure. The temperature variation is something like, oh no, I have already written the quotient here. So this is something in the order of 10 to the minus 3. Yeah? So it's much bigger than what I've said here. So this refers to the case that I have subtracted the dipole. The dipole term is of the order of 10 to the minus 3. It's a dimensionless quantity, right? Everything is dimensionless. And this corresponds to a certain velocity. Velocity of v peculiar, the peculiar motion of the observer here on the Earth of approximately 600 kilometers per second. So that's the velocity with which we on the Earth move with respect to the cosmic background radiation. And as I said, the dipole term was measured already in the early 70s, around 1970. And if you see pictures, then pictures of the whole sky, where the dipole term is shown, so it's something like that. So you have here a hotter part. And on the other side, it's on the back side of the sphere, you have here the colder part. Yeah? And this is the apex of our peculiar motion. This is the direction in which the Earth is moving. Okay, so this is well understood. So we understand that there should be this dipole. It was what one expected. But now if you subtract this dipole, if you consider only the remaining terms from the quadrupole onwards, then actually you would expect that now everything should be isotropic, not in the sense that it should be zero, that this should be a constant here, but in the sense that there are just statistic variations. Yeah? So that there is no preferred axis or something like that for these higher order terms. So this term defines a preferred axis, and this comes from our motion. But here the quadrupole, the octupole, and so on, from these terms one would expect that they do not define particular axes, so that they are just describing statistical variations. So the probability that a temperature takes a certain value here is the same as the probability that it takes this value somewhere else. In this sense, we expect isotropy at this order. And let me write down this quantity first. So this is what is often denoted delta t. So delta t of E is what is left over. Yeah, if you subtract the monopole term and the dipole term, and this is actually what was plotted. I'm sure you have seen these maps which were produced by WMAP and so on, where you have all these little fluctuations. This is what is plotted. It's only this part. The dipole is subtracted usually in these pictures. So this is just the remaining term L from 2 to infinity, M from minus L to L, M theta and phi. And this is what one calls the fractional, because you consider this quotient the fractional temperature anisotropy. So if there's no other systematic effect in addition to the dipole, then you would expect, as I said already, that this would not distinguish a particular axis. So the quadrupole term, the octupole term, and so on would just fluctuate statistically. And you would also expect that this should give a Gaussian distribution. Yeah? So if you measure the temperature in different directions, and you plot the probability with which you find a certain value for the temperature, then you would expect that this shows a Gaussian distribution. Yeah? So if you have the temperature here and you plot the probability, you see, of course, you have a maximum at this mean value, 2.772 or something, and you would expect that then it goes according to a Gauss law to both sides, which would mean that the probability to have a higher temperature is the same as the probability to have a lower temperature. Yeah, so that it is symmetric with respect to deviations from the mean value. Actually, this is usually called the expectation value. I think this is a bad word. Actually, in this case, if you have a symmetric distribution with a maximum in the middle, then the word is reasonable. But you may have distributions like that, right? If this is the distribution, then your expectation value would be here. Yeah? Or if you throw the dice, yeah, you know what the expectation value is if you throw dice. I'm sorry?
Six-sided die. Six-sided die.
Six-sided? I don't understand that.
Six-sided dice. Is that what you're asking? The expectation value for throwing a dice.
Yeah.
With 6 sides.
With 6? Yeah, of course. I use it with one. Yeah. Other kind of dice. 3.5. Yeah. Would you expect to throw 3.5? I wouldn't expect this. So it's, I think average value or mean value is actually the better word. But also in quantum mechanics, we always say expectation value. So, but in this case, if you expect a Gaussian distribution, then of course it is reasonable to call it the expectation value, and for the cosmic background radiation, it's of course these 2.772 or 73 kelvins. And the other question which you could ask is that if statistically it is isotropic. So I say statistically because I do not mean that the temperature is really a constant. Yeah, that would mean it is isotropic. Statistically isotropic means that the probability is isotropic. Yeah? So that you measure a certain value in this direction is the same as in a different direction. And these were two questions which were investigated by WMAP and by Planck with very high accuracy. And actually, there was a claim after the first data from WMAP were published, and later this claim was even corroborated by some people that there were non-Gaussianities, so that you see deviations from the Gaussian feature. But this is still under debate, and whereas inflationary people, they have problems with non-Gaussianity, because if you really assume that there was an inflationary period at the very early stage of the universe, then this should have smoothed out any systematic deviations from just random perturbations, so that everything which is left, everything which should be observed now, is just statistic fluctuations, and then you would expect a random distribution, a Gaussian distribution. So if this is true, that actually there are non-Gaussianities, which some people claim that they have been seen, then one would have to ask for an explanation for this. But as I said, this is not really established until now. And also, maybe you have heard about this, that also it was found also by WMAP and then corroborated even by Planck, that you have beyond the dipole term, you have also anomalies, large-scale anomalies in the next terms. so which are not just statistic fluctuations, but rather something like preferred axis. And actually this was observed with the quadrupole and the octupole term. Both of them seemed to indicate that there's a preferred axis in the universe. And actually this axis has also something to do with the ecliptic of our Earth, which is very confusing, yeah? The plane in which our Earth is moving. So this preferred axis, this was named the axis of evil. Maybe you have heard this. It goes under this name in the literature. You know what it refers to. This was in the, well, I don't know, 2005 or 2006 or so. This was a few years after George W. Bush had delivered this famous State of the Union address, where he called, what was it, Iran, Iraq, and North Korea, I think. The axis of evil, right? So the countries which are a terroristic danger for the United States, and so this was fresh on the minds of people when this anomaly was observed, and so it was also called the axis of evil. It's not. It seems to be statistically significant, so there seems to be really some indication that there is this preferred axis. But there's no explanation until now for this. And probably you have also heard that some people found in the pattern some, but this is more on the jocular side, that they found some shapes, some patterns. So what you see is, if you plot the temperature distribution, you have blue and red or whatever color code you are using, little spots. And some people discovered the initials of Stephen Hawking in this pattern. Actually, it's quite characteristic that you have an SH at one point. Some people discovered a donkey or a parrot or things like that. So it's like this, what is it called, the Rorschach test, what psychologists are using, right? So they are producing with ink, they're producing a certain spot with an irregular shape, and then they show this to the patient and ask him what he is seeing in this picture. And I don't know, some people recognize the face of a mother or a naked woman or something like that, and then the psychiatrist would draw his conclusions from this. And it's somewhat similar with the pattern of the cosmic background radiation. But this is more on the jocular side, of course. But this, the axis of evil could be something true. So it's something which is waiting for the explanation. Okay, so but if we assume that there are no further systematic effects, this is what one calls anomalies, right? So if one sees beyond the dipole term some deviations from a statistical distribution, this is what is called an anomaly. And then I would like to have an explanation where it comes from. There's also a cold spot. Yeah, apart from this dipole thing, there's a certain point in the sky which seems to be colder than the average. This is also one of these anomalies which is discussed. But if they are not there, so if we assume now that everything is just statistic fluctuation, so if we have Gaussianity, and we have, at least statistically, something isotropic, then the thing you would analyze is you would analyze a correlation function. Yeah, that's the only thing which could give you some information. Because if there are no preferred directions and the distribution itself has no characteristic features to tell us about the universe, so the only thing we can analyze is a correlation function. And if you have a Gaussian distribution, then the nice thing is that you have to consider only the 2-point correlation functions. Yeah, usually you have 2-point, 3-point, 4-point, and so on. And in general, they are independent of each other. If you have a Gaussian distribution, then the 2-point correlation function tells you everything. So you are done by just analyzing one expression. So let me remind you, I trust you have encountered this in some course. I don't know, when evaluating measurements or something like that. So the 2-point, what I mean is the autocorrelation function. One very often just says correlation function. What one means is. So what is this? So we have now this function. How did I denote it? Delta with index t. Yeah. When I think usually one puts the index up, because in a minute we will need also the index L. So let me write it in this way. And then I put the L, here's this little L, I use this as a lower index and the T as an upper index. So you have this function, yeah, which gives you the distribution of the temperature on the sky. And you can now form these expressions, where E and E prime are variables which vary over the sky. And if you average this out over your statistical ensemble, then that's what one calls a two-point correlation function. Now we assume Gaussianity and isotropy. And if we have isotropy, this means that what matters is not the position of these two vectors, E and E prime, but only the angle between them. Yeah? If I consider 2 points which make a certain angle in the sky in this direction or in this direction, it shouldn't make a difference. If I have isotropy, if all points on the sky have equal rights, then it suffices. Then only the angle between these two things should matter. So the angle between these two things, they are unit vectors, is just it's just this here. Yeah. So the cosine of the angle between these two unit vectors is just the scalar product between them. You remember how the scalar product in Euclidean geometry is defined? It's the modulus of this times the modulus of this times the cosine of the angle between them. So that's the formula. So this expression should then depend only on theta. So it should be a function only of theta. For a general distribution, it's a function of E and E prime, which vary independently over the sky. But if I have isotropy, it's a function of theta, and this is what one calls the correlation function of, the two-point autocorrelation function of the temperature distribution. It's a function of theta alone. Yeah? But if it is a function of theta alone, then I can expand it with respect to these basis functions here. And, well, I have the situation like here, but now something which is independent of phi. It only depends on theta. Yeah? The function which I now have depends only on theta. This means that, that these things here do not play any role. So I have only the case with m equals 0 to consider. And then I have the dependence of cosine theta in these basis functions. And if m is equal to 0, this reduces to the ordinary Legendre polynomials. So if I want to expand this as a function, with respect to a basis, then the appropriate basis is just the Legendre polynomials. Yeah? So if it would depend on phi, I would use a Fourier expansion. Yeah? Then I would just expand in terms of the e to the m phi. Because it depends on theta, I express theta, I use the cosine of theta as a variable. So I'm now on the interval -1 to 1. And on this interval, the PLs are the natural basis. And there are coefficients now. And so L goes in general. Well, actually, we have already subtracted the first terms. But anyway, let me write L from 0, even if the terms are not there. And then you have coefficients here. And the coefficient is usually written in the form 2L plus 1 over 4 pi. And what we have here, these coefficients, this is what is called the power spectrum, the angular power spectrum of the temperature distribution. So CL of t, yeah, the expansion coefficients of the CT with respect to the Legendre polynomials, this is called the angular power spectrum. Well, you may identify it with a coordinate theta if you choose one of these vectors in the z direction. And because we have isotropy, you are free to do this. Yeah? So if you evaluate this, you may assume that this is just the vector 0, 0, 1. And then this is just, or let's say this is 0, 0, 0, 1. And then this theta is just the theta coordinate of this unit vector. Yeah? So in this sense, well, I should say that actually these coefficients are not defined in this way, but they come out in this way. Yeah. So that it is one way in which you could define them, and I think for the purpose of this lecture, I think it's the easiest way to characterize them in this way. And that's what people measured, what the Planck, the WMAP satellite and the Planck satellite measured. Yes?
If I compare to those points, is there a square root 4 pi divided by 12 plus 1 into this, directly to the CLT, or?
Sorry?
Yeah, we have the square root of 12 plus 1 divided by 4. Is this basically we expand it such that we get them as 12?
Where do you see a square root? Here in the Y's. Here? That's what you're referring to, or where do you see a square root?
Yes, there's a square root.
There's a square root. That's right. Yes. Well, this factor comes from the normalization of the Y's. Yeah. That's how you calculate it. So in the beginning, you write here a factor. I don't know, CLM or whatever you call it, or BLM or whatever, and then you calculate the scalar product of two basis functions. And you see it's proportional to these Kroneckers with a prefactor. And then you choose the factors in front of these functions in such a way that this prefactor becomes 1. That's how it is determined.
Actually, this wasn't my question. The question was, there we have 2L plus 1 divided by 4 pi, and there we have the square root of this term. Do we just expand it like this, then put the other square root term in the CLT?
Do I understand this correctly? Has this something to do with the question in which way these things are normalized? They are also normalized in a certain way, now on the interval -1 to 1. Yeah? And well, this comes actually from the normalization factors. So for our purpose, it's completely irrelevant what this factor is. I've just copied it in a way that I'm in agreement with the literature. You could call this here. You could call this here the angular power spectrum. It would be completely equivalent, right?
So we are expanding now not on the whole sphere, but on the theta angle, right?
Yes.
So there's a difference why we don't have Y's that are.
Exactly. So we are on the interval -1, 1. Yeah, because only the angle theta matters. The phi is there's no phi dependence because of our assumption of isotropy. Yeah. And well, I cannot normalize these functions in my head, so I don't see if there's what kind of factor I need. I just hope that I have copied it correctly from the literature. Okay, anyway, but as you mentioned, the PLs are actually also normalized in a certain way. So we can use this normalization condition in order to solve this equation for the coefficients, right? It's the usual way if you have an expansion in terms of an orthonormal basis. You take the scalar product with respect to another basis element, say PL prime, then you use the orthonormality, so you get a Kronecker here, and this picks you out this coefficient. And then on the other side, you have an integral over C. I think, yes, I've written this here. So integrating over PL prime of cosine theta yields that these you can then solve for these coefficients. There are also funny factors. That's just a 2 pi. Just a 2 pi. Integral, well, the theta runs from 0 to pi, right? Yes. The C T of theta, okay, I multiplied with this, maybe I should write it in this way. This is PL, of course, PL prime. Cosine theta, and then the length element, which is sine theta d theta, right? Yes, that's it. So if you give me your 2-point autocorrelation function, this is something which can be measured, yeah, and which has been measured by these satellite experiments. So you measure the correlation in different directions in the sky. Then from that you can determine these coefficients in this way, yeah, just by integrating over the Legendre polynomial. And as I said, this is precisely what WMAP and Planck have done. And what did they find? Well, this is plotted usually in the way that you plot the L as if it were a continuous variable. Yeah? Actually, L takes only integer values, but if you take all integer values here up to, I don't know, 1,500 or something like that, and that's what Planck did, then it becomes more or less a continuous variable. Yeah? And here you have these CLT, these coefficients. Yeah? So you plot them as if it were a function which depends on a continuous variable L. And well, the result was quite spectacular. Well, if there were absolutely no correlation between points in the sky, so if the fluctuations would not single out a certain angle of separation in the sky, if it were the same for points close together and points farther apart, then this would just be a constant. Yeah? But you see something else. You see, well, the measurements are rather unsure for very small values of L, but then you see a very characteristic maximum, which is around 200. This was first observed by the balloon experiment boomerang, actually. This was the first observation of this so-called first acoustic peak. I come to the possible explanation of this in a minute. And then the satellite missions, they also observed 2 more maxima. So we have now 3 maxima observed. And this goes, the observation goes, I think, up to 1,500 or something. So we have now really a high resolution, right? Last time I told you that Kobe had a resolution of 7 degrees. Yeah? If you have a resolution of 7 degrees, of course, there's no chance to analyze the higher order multiple moments, yeah? Because they describe variations on very small angular scales. But now this, in particular, Planck had a very high resolution, and Planck was able to extend the observations to much bigger values of L. So what does this mean? This means that there's a certain angular scale. Yeah, the L, these polynomials, they are polynomials. So if L is small, they have just, I don't know, 1 extremum, then 2, 3, 4 extrema, a very small number for small L. But for big L, they have a lot of extrema. Yeah, so they oscillate very strongly. So they vary on very small scales. And so for L equal to 200, we have a certain angular scale which corresponds to this in the sky. And it's a fairly small angle. And this is obviously preferred in a certain way. So there's a certain, if 2 points in the sky have this particular separation, then there's a certain correlation between them. Yeah? This does not distinguish particular points in the sky, but angular distances, angular separations. Yeah? The thing is, everything is isotropic. That's the assumption, if we don't talk about the axis of evil and things like that. Everything is isotropic, but we have a correlation between points depending on the angular separation. And actually, when this was observed by boomerang, it was they looked for it. They looked for it deliberately because it had been predicted. And it had been predicted precisely at this value of L. So this here is a so-called first acoustic peak. And how does this come about? Why do we expect something like that in the cosmic background radiation? Well, the theory which is behind this goes beyond the theory which we have until now. It needs a theory which we will begin discussing next Friday. It needs perturbation theory. Yeah? Until now, what we did in mathematics, in the mathematical formalism, was based on the assumption that we have a Robertson-Walker universe. In a Robertson-Walker universe, there are no anisotropies. Yeah? So in order to describe the anisotropies mathematically, we need to introduce perturbation theory. And how do you do this? Well, you assume that you have we will do this. We will begin on next Friday with this. We have a Robertson-Walker universe as a background, and then we have small perturbations of the metric and of the densities. Yeah? So they are not perfectly homogeneous. So the metric is not precisely a space of constant curvature on each time slice, but it has a small variation. And also the density is not precisely constant on each slice, it has a certain variation. And now, if we have such a theory, now you can imagine that we should, or we can start thinking about the question of how this correlation should come about. And the idea is the following. Jumping ahead, we will be talking about the theory later in a little bit more detail. If you have an overdensity, if the density is no longer homogeneous, if you have an overdensity somewhere, what will happen? Well, we are now talking about the time before the surface of last scattering. We are talking about this time here, where we had photons, we have electrons, we had protons, and they were interacting with each other. So the photons had not yet decoupled. So this is, it's a kind of plasma where the photons cannot travel freely. So they are they are coupled to the matter. And now you have an overdensity somewhere. What would happen? It's like an overdensity in a hot gas. What would happen is the gas, the gravitational attraction would make the overdensity even bigger, would attract matter from the neighborhood, and then at some point the pressure would become bigger and bigger, and then the pressure would push everything apart. And what would start is a more or less spherical wave, like a sound wave in a gas, precisely the same way. Whenever you have an overdensity, if it has become dense enough so that the pressure will push it away, a wave will form. And now you can calculate. So your model is you have electrons, you have protons, or other baryons, and you have the photons. And in particular, the photons, they will now, because they are coupled to the matter, they will expand. So they will form a shell. So they will form a spherical wave which expands in the form of a shell. And then the universe becomes transparent at a certain time. And then the photons decouple. So then there's no longer this pressure which pushes them outward. So you have a certain shell which has traveled over a certain distance from the time when the overdensity was formed. And now the question is, can this have any size? So would you have these waves with all possible shapes with the same probability? And the answer is no, because there is a certain time for the thing to travel before the time of recombination. Certain sizes of these bubbles are preferred in comparison to others, and people had predicted that, of course, for this wave, which is expanding, you also do then a kind of Fourier analysis. People had predicted that there should be a large likelihood of such expanding waves of a certain wavelength. That there should be a particular mode which is particularly frequent. The ground mode of these expanding waves, and they could calculate that this peak, which is associated with this first mode, would be in very close to L equal to 100 if the universe is flat. So this analysis strongly depends on the curvature parameter, little k. So it would be in a different place if we have a different k. And when Boomerang found it precisely at this point where it was predicted on the basis of the assumption that k is 0, this was a very strong indication that we actually live in a universe with k equals 0. So it was predicted. So it was what I said now was just the rough idea how these acoustic oscillations come about. Predicted at approximately 200. Actually, it was then after Boomerang had found it. It was immediately after that by another balloon experiment, whose name was Maxima, if I remember correctly. So it was very soon well established that this peak is there from the assumption that k is equal 0. So this analysis, what happens here with these waves in this plasma, strongly depends on the curvature parameter k. And as I said, now WMAP and Planck, they have found the next two modes, which are also approximately where they were expected. So these observations strongly corroborate the idea that we are living in a universe with k equals 0. Remember that the supernovae actually did not give a strong indication for k equals 0. Let me remind you of this picture. That's what we discussed when we talked about the supernovae measurements. Then we had here the curve, the straight line which connects where we have k equals 0, right? If these two things add up to 1, this means that we have just the critical density. So that k is equal to 0. Here k is negative, here k is positive. And then we had the line where the acceleration parameter is 0. So here we have acceleration, here we have deceleration. And if you remember what the supernovae gave us was something like that. Yeah? So actually it was not a strong argument in favor of k equals 0. It was compatible with the data, but actually the most likely values were a considerable piece off this line. It was very, very significant that we are in the domain where we have acceleration. Yeah, so it was very far away from this line. But the relation to the line k equals 0, this was less significant. And now we have these data from the cosmic background radiation, and they favor very strongly k equals 0. In particular, this first acoustic peak was in perfect agreement with the assumption that we live in a universe with k equals 0. And if you combine the data from WMAP and from Planck with other cosmological observations, you get something which is very close here to the line k equals 0, which connects these two values of 1. So we are now, if you take the intersection of these two things, then you are actually very, very close to these values here, which give 0.7 here and 0.3 here. So the observation or the prediction that k should be equal to 0 comes very strongly from the cosmic background radiation. And of course, if you believe in inflation, then this is what we should have. Yeah? Inflation only works if the universe now has k equals 0. Yeah? The curvature, the capital K must be very, very close to 0, so that little k equals 0 is certainly a valid approximation. So the present observations are in agreement with that. So we will talk about these things when we talk about perturbation theory in a little bit more detail, not too much detail, but a little bit more than what I have said now. This was just about the general idea how these oscillations come about, these peaks come about, and whether this is what WMAP and Planck have actually observed. Okay, I'm running out of time, so I think I should make at least a few remarks about the polarization of the cosmic background radiation. I will do this very quickly and not go into detail. Actually, this is something which started only very recently. So I told you that the anisotropy for the temperature is something like 10 to the minus 5. By that I mean, I should have written it here maybe, I meant that these terms here, all of them together, that they are smaller than 10 to the minus 5. Yeah? This is the degree of isotropy of the temperature. Here the polarization is actually isotropic to within 10 to the minus 6 even, so 1 order of magnitude more. Yeah? So what do I mean by isotropy of the polarization? So you see the cosmic background radiation coming towards us. This is electromagnetic radiation. I think everybody knows what it means that electromagnetic radiation is polarized. Yeah? So you have an electromagnetic wave, say traveling in this direction, and you measure the component of the E field in this direction and the component of the E field in this direction, the X component and the Y component. And you ask, are they correlated to each other? So if they fluctuate just statistically, then you say the radiation is not polarized. So every position of the E vector has the same probability. But if they are correlated, then you say you have a certain degree of polarization. So if you have perfect linear polarization, so if the E vector just oscillates in one direction, then of course they would be absolutely correlated, right? If one has a maximum, the other has a minimum, and so on. Yeah. So then we would have perfect correlation. And you characterize this in terms, well, one way of doing it is in terms of the so-called Stokes parameters. Yeah? So there are 4 parameters which characterize the degree of isotropy of an electromagnetic wave. And out of these Stokes parameters, you can then form something which serves as a measure for the polarization, which is unfortunately not a scalar quantity, it is a tensor quantity. And this makes this consideration much more complicated. So the temperature is a scalar. So what we had to do was writing a scalar function as to expand it in terms of spherical harmonics. Now we have, instead of this here, we have a tensorial quantity. So polarization can be characterized by a tensor field, which is usually called PAB. So it has 2 indices. It's a second-rank tensor, and it lives on the sphere. Yeah. On the celestial sphere. And so we cannot expand this in terms of these scalar quantities, which you all know. The spherical harmonics, these scalar spherical harmonics, but there is this generalization of this, maybe some of you have seen this, which are called tensorial spherical harmonics. Yeah? So these are not functions, scalar functions, but these are tensor fields. So they have 2 tensor indices in addition. And there are 2 types of them. One of them are, in a sense, curl-free, and the other ones are, in a sense, divergence-free. So the expansion is much more complicated, and they won't do this here. Actually, I've given the course on gravitational waves 1.5 years ago, I think, together with Klaus Lemmerzahl, and there we talked about these spherical harmonics, these tensorial spherical harmonics in great detail, because they are very important for gravitational waves. But here for this, I don't want to go into this detail. I just want to tell you roughly what you are doing. On the sphere, expand in terms of tensorial spherical harmonics. So as I said, there are 2 classes of them. So you have 2 sums. And the 2 terms have different kind of symmetries, different kind of behavior under inversion of the spatial axis. And this corresponds to the fact that one of them is, in a sense, curl-free and the other one is divergence-free. So you have something like y LM, which have now 2 additional indices, tensor indices, and there are 2 types of them. One usually has an index E, and one has an index B. So as I said, one set is curl-free, and the other set is divergence-free, and this reminds a little bit of electrostatics. If you have an electrostatic field, this is curl-free, it's a gradient. And if you have a magnetostatic field, this is divergence-free. Yeah, it's a curl. And from this analogy comes the terminology that we say the terms which come with these basic vectors, these are the E modes of the polarization, and these are the B modes. It's an analogy. Don't confuse this with the fact that the cosmological background radiation actually is electromagnetic radiation. Yeah? So it has an E field and a B field, but that's not what we are talking about. Yeah, just an analogy. You have curl-free and divergence-free components, and from the analogy with electrostatics and magnetostatics, we call them E modes and B modes. And well, if you do the standard perturbation theory with just scalar perturbations, which we will start on Friday, then you will see that E modes should occur in the polarization, and that they are that we would expect to see them by Thomson scattering. They should come about, and actually they have been observed. So E-modes have been observed, and they can be easily explained on the basis of the standard theory. I think they were observed in 2000, I don't know, 2003 or something like that already. So this is something like that, around this. B-modes were not observed for quite some time. They were observed in 2013, and they could be explained by lensing, gravitational lensing of, which influences the light on its way, on the way of the cosmic background radiation fairly shortly before it reaches us. So it's something that happens on the way of the photons, when the photons are on the way towards us from the surface of last scattering. And they were observed, this was a famous observation in 2014, where the signature was of a different kind, and it could not be observed. The people who observed this claimed that this is not of the kind which can be explained by lensing, and they explained that this was wrongly explained as coming from primordial gravitational waves. So this was the bicep 2. This was, what is it called? Something with polar bear, I think. Yeah, who observed this, the B-modes for the first time, but without much media echo, because it was something which was explained in a rather non-spectacular way. And this was bicep 2. Yeah, this was this instrument which is it is dismantled now, but it was at the South Pole, and which observed these B-modes, which, as the people claimed, would be an effect from primordial gravitational waves. So this is something which is produced on the way of the photons towards us after they have left, long after they have left the surface of last scattering. And here the idea is that this is an imprint of primordial gravitational waves. So gravitational waves which have come about by quantum fluctuations at a very, very early time of the universe. And now, by inflation, these tiny variations have become so big that they make a measurable imprint, that's what they claimed, at the time when the cosmic background radiation comes into existence. So this was something which was imprinted already here. That was the idea. It comes from gravitational waves which existed much earlier. And actually many people suspected that this was an error, because most people believe that they are there, these primordial gravitational waves. But actually one expected that their amplitude was so small that they couldn't be observed in this way. That's what most people thought. And well, after a while it was found that this signature could be very well explained by dust, which produced these effects, again, on the way of the photons towards it at much later times. They had nothing to do with these early times. So the polarization observation is something which is going on now with high intensity, and which will certainly yield additional information about the cosmic background radiation. So, well, it was not this spectacular verification. If it had been true, then this would also be a very, very strong, almost unquestionable evidence for inflation. Yeah? Because if there had not been an inflationary period, then it would be absolutely not understandable how these perturbations had a chance to grow to a size that they can be observed now. So you really need inflation in order to make this so big that it can be observed. But yeah, it wasn't true. So it was neither a verification of gravitational waves nor a verification of inflation. As I said, until now there is no really direct evidence for the existence of inflation. It's just from theoretical considerations that people believe they can explain things in a better way if they assume that this inflationary period was there. And everything is consistent if you assume this until now, but there's no direct evidence. Okay, now I have 8 minutes, so should I say something? Yeah, maybe just a few sentences about other observations, and then I drop this issue and begin next time with perturbation theory. So let me just make a few remarks about other observations. Let me cut this very short. So the most important types, the two types of observations which are most important for cosmology are the Hubble law, in particular the supernovae 1A projects, and the cosmic background radiation. But there are a few others. So for instance, there are also number counts. What's the idea? You just count galaxies. And you count them independent of the flux which they send to us, of their brightness. So you count all galaxies which are brighter than a certain limit, and you see how these numbers depend on the flux, on the brightness. So what would you expect in a Euclidean universe, an Euclidean time independent? Euclidean time-independent universe. So just our naive geometric ideas of a universe which we had as a child. In a Euclidean time-independent universe, there would be the number of galaxies. The number of galaxies n would be proportional to the radius in which you look for them, right? So if you make the radius, you look inside a certain spherical region, and if you make this region bigger, then the number goes with r cubed, with the volume, if the galaxies are distributed equally. And the flux f, of course, is proportional to r to the minus 2. The farther the things are away, the smaller the flux. Because the flux falls off with 1 over r. So if you combine this, then you see that n is proportional to f to the power minus 2 over 3, right? So you expect a correlation between the number which you count and the flux which you use as a limit for the observations in this way. And where the flux is associated with a magnitude, with what astronomers use for the brightness of sources by a logarithmic law. So for this reason, you usually consider log n, which is then minus 2 over 3 log f plus a constant. Okay, so that's what you would expect in a Euclidean time-independent universe. And now we are not in a Euclidean time-independent universe. We are in a universe which is expanding, and maybe it's also spatially curved, and then you would have a different law. And that's what people try to observe. So they observe the relation between, so this here is a magnitude, it's proportional to the magnitude. The factor is, I don't know how it is related to the little m, to the magnitude, but up to a numerical factor, this is just the magnitude. And this is what one tries to observe. And so you make a particular cosmological model, then you have a prediction how the volume changes and how this law should change. For this you use the luminosity distance, which up to the redshift factor is the same as the area distance, and the numbers you can just count. And in this way, you can also restrict your models. You can see if you have a particular model, for instance, lambda CDM. Here you assume that you have a cosmological constant and the matter with the density which we believe in now, and you have a certain prediction for the relation between these two things in this model, and then you can see if it fits the observation. Actually, these things are not very precise, and the problem is that actually if we look farther out, then we see galaxies at an earlier age. The galaxies which are far away from us, they are seen at a younger age because the light needs a certain time to travel towards us. And galaxies at a younger age are physically different from later galaxies. So there's a certain way in which galaxies evolve over time. And this destroys, in a sense, this analysis, yeah? Because we need to know how the brightness of a galaxy is related to its age. And this is not very well known. And this is not easy to calculate this effect out of the data, to remove it from the data by calculation. That's the reason why these number counts are not very strong, do not give very strong restrictions on the cosmological models. At least I think one can say that they are in agreement with what we have, what we believe in nowadays with the lambda CDM model. So there's no contradiction to the lambda CDM models. So this is one thing which I wanted to mention at least briefly. Then there are the so-called baryonic acoustic oscillations. Usually abbreviated BAO. What is this? Well, I talked about these waves which came about from overdensities. Yeah, if an overdensity formed at a certain time before recombination, then a sound wave would start propagating. And I talked about the effect on the cosmic background radiation, that this would leave an imprint in the cosmic background radiation, because the photons take part in this motion. But not only the photons take part, also the baryons take part. So also the distributions of the baryonic matter should show an imprint of these waves. And that's what is called baryonic acoustic oscillations. And people have looked for this in statistical data on how galaxies are distributed in the sky. In particular, what was called Sloan Digital Sky Survey. Yeah, Sloan. This was a big project where many galaxies have the redshifts were measured and the positions were measured. Digital Sky Survey, a big survey over a large part of the sky. And actually, people claimed that in these data they found an imprint of these baryonic acoustic oscillations. So this is something which has also made contact with observations. So it is exactly the same as acoustic oscillations in the cosmic background radiation, but now for the distribution of the baryonic matter, which acted as seeds for the formation of galaxies. Okay, I just wanted to mention this very briefly because you might find it in review articles and something like that, where our knowledge of the present universe is reviewed. And then I already mentioned lensing, but there's one feature of lensing which I have not mentioned until now. So I talked about microlensing, which gives you a good idea of how many machos there are in the halo of our own galaxies. I have talked about weak lensing in galaxy clusters. Yeah, so we looked at the bullet cluster, where we have calculated the surface mass density, and this tells us where the majority of the mass is situated. So this is done since many years towards galaxy clusters. So you see a galaxy cluster in the sky, you analyze the shape of the background galaxies, and then you get the surface mass density in this direction. Only the surface mass density. You cannot get from the lensing data alone really the distribution in space. You only get the projection onto the plane perpendicular to the view line. And now you can do this also in directions where you don't see a galaxy cluster. Yeah? So just in the directions between galaxy clusters. And you can probe the distribution of matter on a really large scale in the cosmos. So I cannot squeeze it there, so let me write it here. So this has also been done, weak lensing on a large scale. I'll put it this way. And in this connection, this in particular the catchword cosmic shear can be found. So what is meant by that? So if there's no galaxy cluster, then you might expect, or it's a possibility to assume, that then, it is perfectly random. So there are no particular deviations from a perfectly random distribution of the shape of background galaxies. Yeah, so you have elliptical images. They are distorted by the intervening matter, but it is completely random. Not like around a cluster where you have this elongation around the central mass, and you have certainly there's a certain deviation from a homogeneous distribution, clearly shown in the pictures. So you might expect that on large scales everything is homogeneous, but this is not the case. Actually, there is a statistically significant deviation from a statistic distribution, and this goes under the name of cosmic shear. Shear means that the bundle is distorted, so that you have, if a light bundle starts with a spherical cross-section, a circular cross-section, and now it goes through matter, then it is distorted into an ellipse. And if this doesn't average out over certain regions, then you say you have at cosmical scale, you have a certain shear. And that's what is meant by this. And this has been measured. And this indicates that at large scale, you have not a homogeneous distribution of matter. So if you average out, even over large scales, over many galaxy clusters, and not just considering neighborhoods of a particular cluster where you have certainly a certain overdensity, that even then you have deviations from a uniform distribution. And this has been used in combination with other observations even to map the matter distribution on very large scales. There are also pictures where you have these filament structures over large areas in the universe. This comes from weak lensing. And this is also something which has to be explained by, or must at least be in agreement with, cosmological theoretical assumptions. So I think these are the most important types of data which we have, which we have to match if we do theory. This was a very brief overview on these observations. Certainly somebody who is involved in observations could have done this at much deeper depths, so at a much deeper level. So I'm a theorist. I feel much more comfortable when I talk about theory, and that's what I will start about again next Friday when we do perturbation theory, in order to put some of these things on a solid mathematical basis. Okay, see you on Friday.